Well, here we go. We're going to be talking about Chapter 2, and what we want to really understand is things that go around in circles so that we can talk about roller coasters. So I'm going to begin. They talk about windmills in your book, but I'm going to go straight to something that I think shows the ideas a little bit better, and that is a teeter totter. If we have a small human creature who is sitting, let's say we'll try and draw our small sitting human creature and holding on to the teeter totter here, and let's say that our human creature weighs this is a pretty small human creature, maybe 100 newtons, and this person, we can say their center of gravity, which I'm going to denote in blue. And center of gravity is something you've got to feel for. I mean, it's pretty much about where the center of their body is. It's what they would spin around if you took that person and flipped them over. If you had, let's say that you had a something like a bowling ball pin or something like that, and it was heavier in the middle or at the end point right here, and you threw this thing, it would revolve around the very center of gravity, right? So it would spin, it would throw like that, and it would be revolving and turning right around the point that you've got equal weight on this side and an equal weight on this side. So anyway, this, well, call it a little girl, her center of gravity, she's got some on, a little bit in front of that center of gravity, a little bit behind, but we'll call it her center of gravity is right kind of in the middle there, and that has 100 newtons of weight pushing her down. Of course, the teeter totter is pushing up on her with 100 newtons, but that's what keeps her from falling down. Now let's say that she is, we'll call this a really long teeter totter. We'll say it's between here, this point, and right there, it's going to be 2 meters. Okay, now you're imagining, so this teeter totter is sitting here. If she sat down on this teeter totter 2 meters out, well, the teeter totter would want to go, let me put this like this, it would want to go like this, down like that, right? If she was there. But hey, we're not letting it do that, because instead of the teeter totter going down, we're going to have somebody on the other side. So let's say we're going to put a larger humanoid sitting on this side, kind of holding on, and we're going to say that humanoid is 200 newtons. That's a heavier humanoid. Now if you think about it, that person, the heavier person, has got to be sitting a little bit closer to the center of the teeter totter, because otherwise that person is going to make the teeter totter go kind of up like that, right? And we don't want that to happen, so I shall erase that. There we go, I'm erasing. And now, as it turns out, what I have to do to make it so that this teeter totter actually stays level is the weight on this side, which I'm going to call F perpendicular. That's what that little kind of upside down T means. The weight on this side times this distance, which I'll call R1, and we'll call this F1, has got to be equal to, on this side, the F2 perpendicular R2. So whatever this person's weight, which is 200 newtons in this case, times this distance in between is got to be equal to the distance on this side times that weight. Oh, well, that's pretty easy. It turns out that this quantity right here, F times R, is torque. And we abbreviate that with this kind of funny looking T, which is Greek T. And that stands for the torque. And this also, of course, is the torque. Right? So this is torque 2. And the two torques have to be equivalent to one another for this to balance. Makes sense. We need some weight going down, but depending on how far out that weight is, it gives us an indication of the torque, and the two torques have to balance. Now, you might say to yourself, okay, yeah, sure. Okay, well, what are the units of the torque, right? What are units of torque? Well, let's look at this. This is newtons, right? The F is in newtons, so must be newtons. And what is distance, which is R? Meters. So units of torque are always in Newton meters. Okay, now, quiz trick alert. So note this down. Remember that torque always is in Newton meters. Energy, which is force through distance, is in joules. Right? So you should think, you're thinking, well, wait, force is newtons, meters is distance, right? So shouldn't they be the same thing? No, we never write it in terms of Newton meters, even though it really is Newton meters. If it's energy, we write it in terms of joules. So that's the way it works. If it's torque, even though it has the same units, we write it in terms of Newton meters. And we just do that to kind of keep track of what's going on. We know if we see something in Newton meters, it actually is indicating something to do with spin, right, with rotation. And energy, well, that's really joules, so we don't want to be talking about something related to rotation. So it's usually context dependent, and it all makes sense when you start practicing it a little bit. So let's say I gave you a problem and I said, let's see, we're going to have a teeter totter, and we always have, let's see, I'm going to put a distance here. Here's our humanoid. We're going to make our human sit right at the very end here. There's the distance is going to be, let's make it 3 meters. This is a super long seesaw here. And this person is going to weigh 50 newtons. Is a bizarrely small person. Okay, but that's okay. And let's say this person right here is, let's see, I'm going to make that a very tiny person of 10 newtons. And, well, no, let's make him 30, because otherwise I'll have something funny going on. Okay, so let's see. What I want to know is how far out must that person be sitting to actually keep this teeter-totter level. The way we'll do that is put our equal sign right under our teeter-totter, and we know that R times F normal on this side is going to be 3 times 50. Right? That's how many Newton meters we've got on that side of torque. And this side, it's going to be something, which we will call X. Ooh, maybe I shouldn't call it X. Maybe because I've got that X over on the other side. We'll call it Y. times 30 is equal to, okay, so this is basically our Newton meters on this side, the torque on this side, and the torque on this side. So did you see how I set that up? This is my R, this is my F on this side, and there's the R and the F on this side. So we've got our equation set up. We can figure out how far out this person is by just solving this, and we'll solve this by dividing by 3, or 30 on both sides. And let's see, this becomes a 1, of course, so we've got y times 1, which I'll just write as y, is equal to, and let's see, we've got 150 divided by 30, and that gives us a 5 meters. So this is actually a little bit misleading, you know, just in how I drew it there, because this side should be a little longer, but it's 5 meters here, 3 meters here, and that's how we can balance this lighter 30 Newton person with a 50 Newton person on that other side. So let's just do one more really quickly. So to make things quicker, I have actually set it all up here for you. Look, we've got a person who weighs 20 newtons on this side. They're sitting 5 meters out on this incredibly long teeter totter. And they have a person on the other side who's only 1 meter from the end, right? And we're trying to figure out how much does this person weigh. So all we have to do is take force times the distance, that's the torque. So we're going to have 20 newtons times 5 on this side. And on this side we're going to have, let's see, some unknown we'll call y, weight. That's our perpendicular force, times 1 meter. And now we can solve for y. Oh golly, this one's really easy. So we'll divide this side by 1 and this side by 1. 20 times 5 is 100. Divided by 1 is 100. And 100 is equal to y. Is that right? Yep. So what does y have to be in units of? It was the weight, so it has to be in terms of newtons. So we've just solved for that person's weight in newtons. So the upshot is, whenever I give you a problem that has to do with teeter totters, you always just set it up so that it's the radial arm on one side, right, times the weight at the end of the one side, and that's got to be equal to the radial arm on the other side times the weight on the other side. As long as you set that up, all I have to do is give you any 3 of those 4 values, and you plug them in and then solve for the 4th value. It's pretty darn easy. Now what all of this is talking about is translational versus rotational energy, or rotation, sorry. So what we've been talking about here is translational versus rotational motion. What's rotational? Well, you're just going around in a circle. And kind of a teeter-totter, that's actually what it's doing. What it would like to do is just keep going all the way around in a circle. If it didn't hit the ground, right, it'll go this far. Oops, I'm not drawing this very well. It'll go this far, but then it hits the ground, so it can't rotate anymore. But it would like to. So the motion we're talking about is actually rotational motion. What is translational motion? Translational just means you're going from A to B straight. A to B straight. And that's translational motion. Okay, so now another thing we need to know, and I'm sure you've seen this before, is just as we needed for translational motion, we have meters, right? Meters are our unit for that. Well, for rotational motion, we need something similar to that idea. And what we use is radians. Well, that's the SI unit. That's the same as degrees. We all know 360 degrees makes a circle, but actually 2 pi radians makes a circle too. So for angle, we often use theta, and that means the angle. And we can have theta in degrees, right? So we can say something's at, well, 90 degrees. Or, right, if this is 0 degrees and then going through here would be 90 degrees. Or we can call this pi over 2, right? Because if we went all the way around a half circle, and if the length from here to this point right here was 1 unit, then we could take that 1 and multiply it by pi, which is actually 3.14 or something or other, all the way on to infinity. So if this is 1, then to go around this half circle would be 3.14 and a little bit of skosh, right? And that would take us around the half circle. So clearly, if we only went this far, that would be pi over 2, right? There was a state legislature back in the late 1800s, I think it was, who decided they wanted to define the number pi to round it off to be like, I don't know, 3.1, something like that, without all the stuff at the end. The problem with that is, like, that's like saying, I'm going to mandate the length, and instead of it being 3.14 and all the rest of the stuff, it's going to be a little bit less. So guess what? Your circle, see, that was a bad half circle, but this is an even worse half circle. See, it's actually, I'm going to exaggerate it a little bit more. Look, this is what would happen if you made the number a little bit smaller. You don't have half a circle anymore. You have this kind of elliptic or ellipse that's smooshed down a little bit because you don't have quite enough to make it into the big half circle that it's supposed to be. So you can't round that number off. You have to have 3.14 and all the rest of that stuff there to make it into a half circle. And a radian is just a measure for an angle, right? And pi radians get you half a way around a circle. 1 radian would get you around 50, I think it's around 57 degrees. It gets you right about up here. So see that, whatever that length is, if you go around right to here, it'll get you about 57 degrees. And so anyway, angle is one of the ways that we use to quantify circular related motion and circularly related rotational quantities. Now, you know that just as we had distance is in meters for translational motion, and we've got let's see, rotational motion is angle, and we've got, oops, I don't know why my, so angle, and it's going to be in radians. And radians is actually, it's kind of like a quantity that doesn't really have units. So we'll say it's actually sort of technically unitless because it's sort of a ratio. Okay, so, but we still call it radians. So, okay, so if we have distance, it's in meters, angles are in radians, velocity is in meters per second for translational, and for if we have something that's rotating, of course, it could rotate with some kind of velocity, and so that's going to be in, well, here we go, velocity, angular velocity, angular, and that's going to be in radians per second. Just like this was meters per second, this is radians per second. But sometimes because it is unitless, we'll just say 1 per second. That means 1 revolution per second. Acceleration, we are all kind of used to that now. That's meters per second per second. And angular acceleration, is in radians per second. Or, since it's unitless, we can say 1 per second per second. Okay, we're finding all these relationships between translational quantities and rotational quantities. There's one more. And that is, we know translational, we learned about mass, which is the same as inertia, right? Inertia, if I can spell it right. Rotation has inertia as well. If you've ever tried to spin a bowling ball, you know it has a certain resistance to you trying to cause it to spin. So what we call this is rotational mass, or sometimes we'll call it rotational inertia. And this is in units of kilograms times meters squared. Now you may think, oh, you know, I can see the inertia is kilograms, but where this meter squared comes from. Remember, whenever you see meters squared, that's like an area, right? We've got some, you know, X and some Y here, so it's actually like an area, And as it turns out, if I tried to spin something that was pretty heavy, but it was the size of a baseball, you know, it'd be like a lead baseball, that would be, you know, it's hard to do, but it wouldn't be too bad. If I took that lead baseball and I spread it out really thin, right? So it would be the same mass, right? Because I'd be mushing it down really thin. But I tried to spin that. Because of the larger area, it would actually be much harder to spin. So that's why this meter squared is in rotational inertia. It's a factor that has to do with how it makes it harder to spin something that's a larger area. You've seen the same sort of phenomenon if you've ever tried to spin pizza dough. When it's the little ball, it's really easy to spin. But as you flatten it out and you try and spin it on your hands, it gets much harder to spin as it gets broader. Now this brings us to Newton's second law of rotational motion. So we saw Newton's second law before. F is equal to ma. That's the translational version of Newton's second law. Okay, so we'll say Newton's second law. So there's translation, rotation. Okay, hold on to your hats here. It is torque is equal to the rotational inertia times rotational acceleration. It's actually the same sorts of quantities here. We've just translated them into rotational terms. So I'll write this down underneath. We've got torque, and this is the rotational inertia. And remember, that was kilogram meter squared. Oh, torque, we should write that down. That's Newton meters. And then rotational acceleration. And that was, well, 1 per per second. Oops, my little pen is hung up here. Sorry about that. Come back. Stop that. Okay, there we go. Per second squared. If we wanted to, we could write radians on the top here, but I'm not going to. I'm just going to call that 1 per second squared. So here we have F is equal to ma. Here we can say that the torque is equal to the rotational inertia times the rotational acceleration. So will we use this one very much? No, not really. It's just nice to see that there's this analogy between translational and rotational. I do like the way your book phrases it, which is that spinning a marble with small rotational inertia is much easier than spinning a merry-go-round, which has much larger rotational inertia. Well, if we're going to do some analogies, we might as well do a few more. Here we go. We know that work is equal to force through distance for translational. For rotational, we can say work is equal to the torque times the angle that you take that torque through, right? So take a torque around some angle, and that tells you how much work you've done. Likewise, if we have kinetic energy, that's just motional energy. We can calculate that as, always write kinetic energy is equal to 1/2 times mv squared. That's how we calculate that. This is the velocity, and this, of course, is the mass. In rotational terms, we can say the kinetic energy is equal to 1/2 times that rotational inertia, I, times omega squared. What's omega? Omega is the angular speed. I actually should have written that up here earlier, so I'm going to put that right here. Here's angular velocity, angular speed, which is omega. Okay, so now you see how that's written. Okay, so now we see yet another analogy. And all of these, I think, just show the real unity between different kinds of physical quantities, which I think is really pretty cool. Okay, now how might we use something like this? Work is equal to torque times angle. Aha! I'm going to show you in a video something called an addle-addle. What we're going to do is we're going to take that addle-addle, which is a huge long throwing spear. It's like 6 feet long. And we're going to move it through an angle. That's how much energy we put into it. And we'll use that to throw spears. You'll see that very soon here. Here's a nice little simulation that shows velocity and acceleration. Both velocity and acceleration are vectors. That means they have a size, right? That's the magnitude of how big it is, and they have a direction. So watch, when I take this little ladybug and I start speeding it up, see how the velocity vector, like when I slow down, it goes backwards. When I speed up, it goes forwards. Now watch, I'm going to take this ladybug around. See, it wants, if I want it to go in a circle, I actually have to accelerate it inwards. Otherwise, I'm accelerating it forwards. Here, I'm going to accelerate it in one straight non-rotational direction. There we go. See how it's accelerating like that? And we're accelerating, oops, backwards here. Okay, accelerating back and forth, and you can see the velocity vector. That's the way it's going. Now watch what happens when I make it go around in a circle. See that acceleration vector is always pointed inwards. That's the force that's making it go around in the circle. It's pulling it inwards rather than letting it just go straight the way it would like to go. Velocity vector, right, is in the direction that it's going in. Acceleration vector is keeping it inwards. So it's a little counterintuitive there. Let's look over here. Rotation, this gives us our angle, theta. Now watch, we're going to take it around. There we go. We're up here at almost 90 degrees. So there's the angle of the ladybug. See how we've changed here over time. You can see the angular velocity, right? And the angular velocity is just the speed at which it's moving. So let me reset everything. I'm going to reset it. Yep. Okay, here we go. We're moving it around. You can see how that angle is moving around there. And let's see, I have a little trouble keeping the velocity steady unless I stop it altogether. But you can see how I've gotten most of the way around. 360 degrees would be all the way around. And here's our speed of our ladybug. Here's the final position in meters, how far we've gone along here. Here's our other critter. We're just taking it around. And you can see again the velocity and the acceleration vectors as we move it around.